I think it'd be worthwhile to print this particular page out because you can label it and then refer back to this as you go through this unit where we're talking about limits, discontinuities, and the horizontal and vertical asymptotes. So I've already indicated over here on the right hand side, first of all, what the different types of discontinuities are. We talked about that in one of the more recent lessons. I've also indicated at what x values along the way does this function f of x have a discontinuity. Okay, so the informal definition of continuous or continuity would be a function is continuous as long as you can draw the graph without lifting your pencil. Okay, so that would be the kind of like the rough definition of it, and that's not certainly a calculus definition, but it certainly gives us a good rule of thumb where you can quickly spot where we have a hole or a vertical asymptote or a jump, kind of where you can't connect the two parts of the graph where you have discontinuities. And so I indicated that here at -4, -3, -2, 3, and then again at 4. We have 5 spots along the way where we have discontinuities, and this graph is great because it gives us all different types of discontinuities. So we can check off part A because we indicated where we have discontinuities here. And then part B, name the type of discontinuity. Well, those are pretty easy as well because we can see the different types over here. Please don't worry about the oscillating kind right now. We'll talk about that later. We're going to concern ourselves right now with the 3 types of discontinuities that we normally see would be the jump, the infinite, and the removable. Important to note here that if it's not a removable discontinuity, then these two here would be considered to be non-removable discontinuities. So there's basically 3 types of non-removable discontinuities, and only 1 type of discontinuity in which it would be considered removable. Okay, so let's take a look at the first one. At x equals -4, we can see that the limit exists. There's only a hole there, so we're going to call that, and that's what we do call it, a removable discontinuity. Okay, where we have a vertical asymptote, we would always call that an infinite discontinuity. Okay, and one other thing to keep in mind, a removable one would be if you can just place your pencil right in one little dot and put a dot to make it continuous, that's going to be a removable one. Okay, so when you look over here at the discontinuity at -2, we can see the function jumps from one piece to another, and that's why we call it a jump discontinuity. But also you can't just put your pencil in one spot to fill the gap. Okay, so therefore that's not non-removable. And then again we see we have another vertical asymptote, so we would call that an infinite discontinuity at 3. And then over here, even though this is kind of confusing in the beginning, where even though we have a dot up here, that's the calculus part, or sorry, that's the algebra part. F of 4 is 1, 2, so we have a point up here at the coordinates 4, 2, but again, that's the algebra part, and the calculus says here the limit does exist. Okay, if the limit exists, then we have a removable discontinuity. Whether or not the function is defined at that x value, it still is a removable discontinuity. Because if that dot weren't there and it were placed right there in the open circle, then we would be removing the discontinuity. And I know this is all brand new stuff, so hang in there with the terminology. Okay, so that's part B. Now part C, for each discontinuity, state why it fails the formal definition. Okay, so it would be important to note that. I'm going to pause the video and write those things down in the upper left hand part of this graph so you don't have to sit and wait for me to do that.